Analysis of trace evidence, applications in forensic chemistry. Title: Analysis of trace evidence, applications in forensic chemistry. Introduction, 100 words. Forensic chemistry is a branch of forensic science that plays a critical role in criminal investigations. One of its key subfields is the analysis of trace evidence, which involves identifying and examining minute amounts of materials found at crime scenes. This article explores the various techniques used in the analysis of trace evidence in forensic chemistry, highlighting their applications, significance, and impact on criminal investigations. The significance of trace evidence, 200 words. Trace evidence refers to microscopic amounts of materials that can be transferred during the commission of a crime. These materials can include fibers, hair, paint chips, glass fragments, gunshot residue, soil, and many other substances. Though small in size, trace evidence can offer crucial insights into criminal activities, contributing to the reconstruction of events and aiding in the identification and prosecution of suspects. Analytical techniques in trace evidence analysis, 400 words. Forensic chemists employ a range of analytical techniques to analyze trace evidence. One such technique is microscopy, which allows for the examination of trace evidence under a microscope. Microscopic analysis can reveal important characteristics such as the type of fiber or the color of paint, which can provide valuable leads in investigations. Another important method is chromatography, which separates complex mixtures of substances for further analysis. Gas chromatography, GC, and high-performance liquid chromatography, HPLC, are two only used techniques in trace evidence analysis. GC separates volatile substances like accelerants found in arson cases, while HPLC identifies and quantifies various compounds, including drugs and poisons. Spectroscopy techniques, such as infrared spectroscopy, EAR, and mass spectrometry, MS, are also vital tools in the analysis of trace evidence. EAR spectroscopy helps identify unknown substances by comparing their infrared absorption spectra with known reference materials. MS provides information on the molecular composition of substances, aiding in the identification of illicit drugs or explosives. Furthermore, DNA analysis is a game-changing technique used in trace evidence examination. Forensic chemists extract DNA from trace biological materials like blood, saliva, or skin cells, allowing the identification of individuals present at the crime scene. DNA profiling has revolutionized criminal investigations by linking suspects to crimes and exonerating the innocent. Applications of trace evidence analysis, 500 words. The analysis of trace evidence has several crucial applications in forensic chemistry. Firstly, trace evidence can link a suspect to a crime scene, providing critical evidence to support or refute alibis. This can be achieved through the identification of unique fibers, gunshot residue, or paint chips found on the suspect or their belongings. Secondly, trace evidence can help establish links between different crime scenes or connect a suspect to multiple crimes. For example, the presence of the same fiber or soil type on multiple crime scenes can indicate an association between these incidents. Such connections are invaluable in building a strong case against a serial offender. Thirdly, trace evidence analysis aids in the examination of questioned documents. Ink analysis, for instance, can determine whether documents are genuine or forged. Additionally, analysis of paper fibers or indentation marks can help identify alterations, erasures, or hidden information. Moreover, trace evidence analysis contributes to accident reconstruction. By analyzing the broken glass, paint chips, and tire marks found at the scene, forensic chemists can determine the circumstance surrounding vehicular collisions or hit-and-run cases. This information is vital for determining fault and understanding the sequence of events leading to the accident. Limitations in trace evidence analysis, 200 words. While trace evidence analysis is a powerful tool in forensic chemistry, it is not without limitations. One significant limitation is the challenge of interpreting trace evidence results. The presence of certain materials at a crime scene does not always definitively prove a suspect's involvement. It is crucial to consider alternative explanations, such as innocent transfer or contamination, when interpreting trace evidence findings. Another limitation lies in the potential for false positives or false negatives in DNA analysis. The sensitivity of DNA testing means that even trace amounts of genetic material can be detected. How? The interpretation of DNA results can be complex, and human error in sample collection, storage, or analysis can lead to inaccurate conclusions. Additionally, the availability of scientific evidence and funding can impact the thoroughness and reliability of trace evidence analysis. Insufficient resources may limit the number of samples that can be collected and analyzed, potentially missing crucial evidence. Moreover, the accessibility of advanced analytical techniques can vary across different forensic laboratories, affecting the quality. Why incomprehensiveness of trace evidence examinations? Furthermore, trace evidence analysis is vulnerable to challenges in court. The presentation and interpretation of trace evidence findings require clear communication to ensure that the jury understand the scientific basis and limitations of the analysis. The ability of expert witnesses to effectively convey the significance of trace evidence is essential in ensuring its acceptance and admissibility in court. Despite these limitations, trace evidence analysis remains a valuable tool in forensic chemistry. Ongoing research and advancements in technology continue to address these limitations, allowing for more accurate and reliable interpretation of trace evidence in criminal investigations. Future directions in trace evidence analysis, 200 words. Looking ahead, there are several areas in which trace evidence analysis in forensic chemistry is expected to advance. One area of focus is the development of more sensitive and selective techniques or the detection and analysis of trace materials. This includes advancements in microscopy, chromatography, and spectroscopy, where the aim is to increase the sensitivity and specificity of these techniques. In addition, there is a growing interest in the application of nanotechnology in trace evidence analysis. Nanomaterials have unique properties that can enhance the detection and characterization of trace evidence. For example, nanoparticles can be used as labels or probes to enhance the visibility or recognition of materials under microscopic examination. Another area of development is the integration of data analytics and machine learning algorithms in the analysis of trace evidence. By applying advanced statistical models and algorithms, forensic chemists can extract valuable information from large datasets, improving the accuracy and efficiency of trace evidence analysis. Furthermore, there is ongoing research in the field of isotopic analysis, which examines the stable isotopes present in trace materials. Isotopic analysis can provide insights into the origin and history of materials, allowing forensic chemists to determine geographic or temporal information that could be valuable in investigations. Lastly, the advancement of miniaturized and portable analytical devices is expected to revolutionize trace evidence analysis. These devices allow for on-site analysis, reducing the time and cost associated with sending samples to a laboratory. Portable devices can be particularly useful in urgent or remote crime scenes where immediate analysis is necessary. Future directions in the analysis of trace evidence, 267 words. The analysis of trace evidence in forensic chemistry is constantly evolving, and there are several exciting directions in which the field is headed. One area of focus is the development of advanced imaging techniques. High-resolution microscopy, including scanning electron microscopy and atomic force microscopy, can provide detailed images of trace materials at the nanoscale level. This level of resolution can reveal even more information about the characteristics and composition of trace evidence, enhancing its potential value in criminal investigations.